right, guys, this is our last video of material we need to cover this semester, and it is sort of a wrap-up video in a way because it's something that APA, the American Psych Association, has in recent years been requiring of all research publications. So if you're reporting your data, your statistics as a result of some analysis you did for your experiment, you not only have to report the results of the hypothesis test the way we've been doing, reporting the t results, the f ratio results, and most recently the chi-square results, but you also have to report a measure of effect size so that the reader can determine not just whether or not your effect was significant and that the two variables are related, but also then the size of that relationship so that they can interpret a little bit more information from the data that you present to them. So we are going to do that now. We've done that a little bit already, so there's just a few things that we need to wrap up with that we didn't really fully cover. So we did talk about little r squared, right? Little r squared is our proportion of variance accounted for, or coefficient of determination, right? We had all these various terms for it, all of them essentially being related to the prediction accuracy of a correlation or regression equation, right? So little r squared is the measure of effect size for correlation. Big R squared is the measure that we use for ANOVA calculations. We've seen how to do that already, but we forgot somebody, right? We started talking about effect size and correlation, and then we stopped talking about effect size while we were in the t-test world. We brought it back in ANOVA, but we forgot Mr. T, right? And so we need to go back and address the effect size measures that are available to us for our t-tests. And doing so, I'm just going to use the exact same examples and data that we did before, so you can easily go back then to those slides and see the larger contextual problem if you'd like to, and how we got to these particular values. But for now, we're going to sort of skip ahead to it. So in this example, we're going to talk about an r squared for independent samples, right? And this can be written as a large r squared or as a little r squared. It's not yet the Cohen measure, it's a different measure, but we can in fact use this in the same way that we use the little r squared for correlation. It means functionally the same thing, the amount of variability in your dependent measure that is explained by your independent measure or your independent variable. So the example that we had talked about in the independent samples t-test lecture was one where we had males and females watch cartoons and then give ratings for those cartoons. If you'll remember, the ratings that both the males and the females gave for the cartoons were nearly identical, and we found that there was no statistically significant difference between these groups. So we probably are not going to find a very whoppingly large effect size here either, right? Because there was, at least in most ways of accounting for it, no effect at all. Okay, so how do you calculate r squared here? To get it, you need t, right, the value of your t-test, your test result. You need degrees of freedom. We have both those pieces of information from our original data. So our t-test back then was to take the average of males, 82.25, subtract the average of females, 82.6, divide by the standard error of the difference, this 11.847, and that gave us a t statistic of 0.03, right, negative 0.03 in this case. We'll just use the absolute value here. We know our degrees of freedom was 7, right? We did not have a whoppingly large sample size here. It was just some people from my research lab, actually, that participated to give us these data. So if we have our degrees of freedom, we have our t, then we can plug them into an r squared formula where we put t squared on top, t squared plus degrees of freedom on the bottom, and we find a super tiny effect size, 0.000128. Our measures of effect size here start being called small when they make it to 0.01. So we have almost a non-existent effect size here, right? But had we had something between 0.01 and 0.09, we'd be in the world of small effect, above 0.09 a medium effect, above 0.25 a large effect. We can use r squared for dependent samples too. Formula, in fact, is identical. You still use the t squared in the same spot and the degrees of freedom in the bottom. So in that particular example, we had been looking at a different score. Remember, in the dependent samples, it doesn't even matter what your original data are because you work then with the difference score in order to calculate your statistics. And so we had a different score in that particular example. It was 11 or a negative 11. And this resulted in a t-test, a t-statistic of a negative 5.720. So if we want to find a measure of effect size for that test, we simply have to plug in our t squared, plug in our degrees of freedom, solve for it. And in this case, we have what we would consider a large effect size, right, coming in at 0.89. There was a pretty considerable difference between the before and after measurements in this example. And so it's not surprising then that our effect size reflects the size of that difference, not just that it's a statistically significant difference. The other one we can do is Cohen's d. So we've already started talking about Cohen and measures of effect size and giving us cutoffs for how we interpret measures of effect size. He actually gave us a measurement in and of itself called Cohen's d that we can use for t-tests. So if we go back to the humor example and we look at our actual data, see Cohen's d requires the average of x minus the average of y, or average of sample 1 minus the average of sample 2, divided by your pooled variance measure, the square root of your pooled variance measure, right? The first thing you calculate on the way to getting standard error of the difference. So we go back into that calculation, and we grab our X and our Y data. We saw that the average for the women was an 82.25 for their ratings of cartoons. The average of the men was an 82.6. So we have our X bars for the numerator there. Our pooled variance measured then by taking the variance of each group and adding them together gave us a 311.878. We then take the square root of that measure in the denominator, and we put our two averages in the top. We end up with a Cohen's d of 0.019. Again, he gives us measures of effect size, and we are below all of them. 0.2 would be a small effect. We are not even quite at 0.02. So just like in the measure of R squared for this example, we find an incredibly small measure of effect size, but that's not surprising because these t-tests, or this t-test was not significant. And so we essentially found no effect, no reliable effect, and Cohen's d and R squared are reflecting that effect then is obviously very small, if at all. So we can also use Cohen's d for the dependent samples. So this time I put the different score data up there because you need the average of the difference score. That was the -11 that went into calculating our t-test result that we saw a couple slides ago. The other thing you need is the standard error of those data, right? The standard deviation of those data. And so remember, standard deviation uses the n-1 calculation. So if you do the x minus the mean squared, you get all that for your sum of squares of 74, and you end up with a standard deviation of 0.4301. Now, if we were calculating the t-test right now, we'd have to divide by the square root of n so that we had our measure of standard error. That's not what we're doing. We're just using standard deviation of the difference score and the mean of the difference score. If you then take the mean of the difference score, divide by that measure of standard deviation, you end up with the Cohen's d of 2.558, right? This is then considerably larger than the cutoff for 0.8, the large effect size. And we see, just like with R squared, we are finding a very, very large effect in this case, right? The manipulation that produced this difference between time 1 and time 2 had a very large effect, not merely a reliable effect, right? I can be reliably late to every meeting you ever have with me, but it only be by a minute. Or I can be reliably late to every meeting and it be by 45 minutes. Both would be considered statistically significant because they're reliably in the same direction, but one is a much larger effect than the other one. So this last set of videos really tried to wrap up things that we do sort of encounter sometimes, and other things that we need to make sure that we calculate to report. So we talked about two different non-parametric tests, variance on the chi-square that can be used when you violated some of the assumptions. We also then talked about a few measures of effect size for t-tests that we hadn't addressed in earlier material. So that's really, as far as what we can fit in a single semester in undergrad psych statistics, the end of the road for us. So all we have left then to finish up would be some sort of exam review, right? We'll figure out exactly the format of that, but make sure that you guys have some opportunities to ask some questions and to do a little bit of preparation. And I'll make sure to give you a little rundown of what the test looks like in preparation of that so you can plan your studying. We will only be covering the last little bits of material, so that's 4 lectures, 3 of them on ANOVA, the between groups ANOVA, the within groups ANOVA, and the factorial ANOVA, right? Emphasis on interactions in that last one. Then we'll talk a little bit about post hoc tests, chi-squared, and effect size. All of these are fair game for the exam. I did tell you, however, that you will only be calculating between groups ANOVA. That means that were you to have to calculate, say, post hoc tests, effect sizes, or chi-squares, they are likely to be in some form of an extra credit on that Yeah, so keep all that in mind. And remember, because we're wrapping things up, it's time to finish up any remaining homework, right? You should now be able to do all the chi-square homework, all the effect size homeworks. And so make sure you've done that and you have them all ready to go to turn in on the final day of class. So thanks, guys. I appreciate it.